In this example, we're going to find the work done by the vector field f. F is defined as 2xy cubed I plus 4x squared y squared j. And we're going to move a particle once counterclockwise around the curve. And the curve boundary is defined by these functions which create a triangular, it's not a triangle, but a moderately triangular region in quadrant 1. First things first, we want to find our region and know what our boundary curves are. So one of the boundary curves is the x-axis. One of my curves is the line x equals 1. So I've got x equals 1. Here's my x-axis. And then the curve y equals x cubed, a cubic function, is going to be curved more or less. You could probably make it look a little nicer like that. But we have this triangular region. And since we are traveling around this triangular region in a counterclockwise motion and making that loop, we can use Green's theorem. So in this situation, I'm going to define my work as the counterclockwise line integral along my curve of m dx plus n dy, which is the same as the double integral over the region of n sub x, partial of n with respect to x, minus partial of m with respect to y, dA. So my m value here is 2xy cubed, and I need m with respect to y. So m with respect to y is going to be 6xy squared. I have one of my partial derivatives, so now I need n. N is 4x squared, y squared, and then n, partial derivative with respect to x, is going to be 8x y squared. So now I just need to set this up. So I'm going to have the double integral. I need to determine my bounds, and I need to determine if I want to integrate with respect to y first or with respect to x. Of course, we're given this function y equals x cubed in terms of x. We have y in terms of x. So I can think about that as above and below, and that would be y equals x cubed on top, y equals 0 on the bottom. And then my x values, x goes from 0 to 1. The only way that this would change is if these were y, if we said y from 0 to 1, and then my x's, we would have x equals 1 minus, we'd be dealing with x equals, we'd have to rearrange that cube root of y. Anyhow, n sub x is 8xy squared minus m sub y, 6xy squared. And then, of course, the way I've set up my bounds, we're going to say dy, then dx. Cleaning this up, my integrand is going to be 2x squared y. So xy squared. So I'm going to pull that 2 in front, and I've got 0 to 1 and 0 to x cubed. And I have xy squared dy dx. Integrating with respect to y first, I'm going to have 2/3, still have the 0 to 1, and that's going to become xy cubed. And we have y equals x cubed. Again, I always think it's helpful when you're writing that there. Y equals x cubed, y equals 0, because it's easy to get confused what you are plugging these two values in for. You're plugging them in for y. So I have 2/3 integral from 0 to 1 of x times x cubed cubed minus x times 0 cubed. That gives me 2/3 the integral from 0 to 1 of x to the 10th dx, which is 1/11th, so 2 over 33 x to the 11th, and we need to evaluate that from 1 to 0. Plugging in 1, we get 2 over 33. Plugging in 0, that last term goes away, and my final answer is 2 over 33. That represents the work done to move the particle one time in this counterclockwise fashion along that path. Let's look at one other example where we apply Green's theorem. In this example, we're going to apply Green's theorem. We're going to calculate the counterclockwise integral of 6y plus x dx plus y plus 2x dy. This integral is set up as our Green's theorem for counterclockwise circulation. So we need to figure out what our curl integral is going to be along our path C, which is created by this circle. This is a circle of radius 2 centered at 2, 3. Here I've brought in our curve. Okay, so you can see that circular path. So by definition, my m value is 6y plus x, and my n value is y plus 2x. Now for this form, I need partial derivative of m with respect to y, which gives me 6, and the partial derivative of n with respect to x, which gives me 2. Setting this up using our formula, that's the double integral over the region of n sub x minus m sub y dA. And this again is from our Green's theorem circulation version. So setting this up, we'll have our double integral along the region. N sub x is 2 minus m sub y, which is 6. That gives us 2 minus 6 is -4. Now I'll take that -4 and pull that out in front. So I've got -4 times the double integral of that region, right? And I actually don't have to set up this double integral because what shape is that region? The region is a circle. And we can find the area of a circle using algebra. It's pi r squared. Since we know the radius of this circle is 2, pi times 2 squared, -4 times the area of that circle, radius 2, pi r squared, which is pi times 2 squared, we get -16 pi is the value we get when we evaluate this integral using Green's theorem. And again, the answer here was -16 pi. As always, email me with any comments, questions, or concerns.